In the next segment, we will have Professor Shigenori Fujikawa from Kyushu University International Institute for Carbon Neutral Energy Research, Center Director for Kyushu University Research Center for Negative Emissions Technologies, to give us the keynote speech, Carbon Neutral and Beyond. Professor Fujikawa, please.
Okay.
I'm Fujikawa. Very nice to meet you all. Can you see my screen? Okay. So, thank you very much for giving me such a good opportunity, and also I get to know such precious activities ongoing in Kyushu University, and I was willing to contribute to this award technically. So I'm really grateful for this opportunity. So now I would like to start my talk. In this SDG award, theme is thinking about carbon neutral, and we are now considering the theme of the carbon neutral and beyond. That would be the theme of my presentation today. So first, I'd like to briefly introduce myself. I'm Shigeki Fujikawa. So I'm a professor serving as the International Institute for Carbon Neutral Energy Research, and also I am also serving as the Director of Research Center for the Negative Emission Technologies at Kyushu University, and I've been specialized in the material development. So first of all, I would like to introduce my institute, the International Institute for Carbon Neutral Energy Research. The mission of this institute is to contribute to the creation of sustainable and environmentally friendly society by advancing fundamental science to reduce CO2 emissions and establish a non-fossil-based energy carrier system. This is a mission of our institute. So we are now our research is focused on the two materials. One is the hydrogen and the carbon dioxide. I think the hydrogen is it's been seen as very important as a green energy, and we are contributing, conducting the research on how to produce hydrogen efficiency, and also how to produce hydrogen using solar energy, and also the suitable materials for stable storage of hydrogen, and how to use hydrogen effectively, and also for the CO2, global warming gas as a part of research, and we are CO2 emission reduction, and also we are conducting basic research on the CO2 capture and utilization of the stable underground storage. And also we are conducting research on developing the materials using hydrogen and the CO2, and also I think that the energy has to be considered as an overall system. So we are also conducting the analysis of the system overall. So as you can see here, that's it's all based on the fundamental studies, as you can see here, such as chemistry and physics, which are fused together. So today we would like to talk about the CO2 reuse and the collection. So of course that the SDGs targets number 7, 9, 11, 12, 13 are relevant to our research. So I would like to ask you one quiz. So how much CO2 is there in the atmosphere in terms of the weight, not the volume? Let's think together. Please take a moment to think about this question. This is not our volume, but the weight I'm asking. And actually, so these tons, I mean, 1 to 2 trillion tons, or 1 to 2 teratons in English of CO2 in the sky. Maybe it's difficult to imagine. But to give you a comparison, it is said that there are about 1.4 billion cars running on the Earth today. And even though the cars weigh 10 tons per unit or 100 tons, but that would be still far less than that of the CO2. So maybe with this, you may be able to imagine a little bit how much CO2 is in the atmosphere. So So the huge amount of CO2 is emitted per year. It is a global figure. And this in 2017, the 32.8 billion tons were emitted globally. And then Japan released about 3% of that amount, about 100 million tons per month, or 12 million tons per year. So therefore, I think that CO2 emission reduction is very important. And this graph shows the trend of annual CO2 emissions in the world. As you can see, that the horizontal line shows the year, and the vertical line shows the volume. And if you do nothing, that's the volume of emission continue to increase. And so the green part is the volume to be reduced. But that's not enough to reduce the global carbon dioxide emission to zero, because the gray part, it cannot be reduced to zero by all the existing efforts. And so this, there is a target to limit the global warming to less than 2 degrees. So we have to follow the blue line to achieve this goal. And to this end, what we should do? Not only just reducing the emission volume, but we have to capture the CO2 that has already released to the atmosphere, which is so-called negative emission. And then by doing so, we will remove this blue, and then we will come out even or to zero or carbon neutral. By achieving that, the carbon emission will be net zero. So still the 1 or 2 teratons of CO2 is still existing in the sky. Therefore, we continue this effort, we can finally start to reduce the CO2 volume on the Earth. So we have to do this technology to capture the CO2 from the air, which is so-called the direct air capture, DAC. So how we should capture the CO2 in the atmosphere. What is difficult about this technology? I said it's a huge volume is existing there, but when it comes to the concentration, it's only the 0.04% in the atmosphere. So I think that we need to come up with the effective methodology to capture this the CO2 in the extra low concentration. And as you can see here, the many technologies are already introduced in the world. For example, the algae and the tidal floods in coastal areas are said to have a high capacity to absorb CO2. So this is known as a coastal blue carbon, known as the algae capture, and also the various rocks and contain calcium and other elements that naturally weather when exposed to CO2 for long periods of time, and accelerated chemical weathering blocks is also being researched to artificially accelerate this process, and direct air capture, and also the biomass is used and burned, and then we capture the CO2 from the burned biomass, and then if it's captured, totally it will come out even or carbon neutral. And also we can use the soil to capture the CO2. And the most promising method is said to be the direct capture. And actually, a lot of active research and development is ongoing, and a huge amount of investment is made on this technology so far. And this is one example. So there's a big fund is installed to capture the carbons in the air, and a company in Swiss, Climeworks. It's been introduced recently in the newspaper in Japan. It has the world biggest direct air capture is now being installed in the Iceland, and it became operational and actually capturing CO2. And so what kind of technology is there to capture the CO2? But there are not so many. There are only 3 are existing in the world, and it's also cost-effective as well. The one is the solution absorption. So the liquid absorption. So the air is blown into the absorbent solution, in which a chemical that reacts with the CO2 is dissolved, and only the CO2 is recovered. Another one is the adsorption solution, and also use the holes with makes the CO2s attached to the small holes. And last one is the membrane separation. These are the general 3 methods. The carbon engineering and the Climeworks, as I mentioned earlier, they are employing these technologies as well. But actually, that's the most of them are based on this solution or liquid absorption technology. So if you use the solution processing this air, like exhaust gas from the factory, is using this technology to remove the acid gas from the exhaust gas. So the gas being processed in the liquid, this technology is already commercialized in the market. So this is highly promising, and actually the venture companies are using this technology, and also they can process a huge volume of the air. But it's not enough. It's not the end of it. There are many problems. But because it requires a lot of energy especially once the CO2 is dissolved in the solution, and then it should be heated, and then it should be captured as the gas format, and then it's buried underground. So you have to heat up the solution. So that it requires a lot of energy, so that we have to reduce the energy consumption there. And also, if you have the wet towel and you dry the towel if you blow the air, but so you put the water in the sponge, and you have to dry this sponge. So it has to require a lot of the consumption of the water. That is another problem. So we use some chemical solution, so that has to be done in the large scale. Therefore, the location that we can install this device will be limited. And so why other technologies are not used for the capturing the CO2? So it's not a direct air capture, but this is a cost of the capturing the CO2 from the coal-fired factory, and then this is 2,000 yen per ton and 2,000 yen per ton, and also 1,000 yen per ton. So it's not commercialized or realized yet. This is an assumption or estimate of the cost. So the coal-fired power generation has the high concentration of the 10% of the CO2, and if we apply the same concentration, the relativity would remain the same. Therefore, the membrane separation could be the cheapest solution.
But why does the membrane separation is not used for DAC? Why there is no such attempt going on, unlike the thermal power station? Because there are big issues related with this membrane separation. This is the David Keys of the Harvard University professor. He is a founder of the companies I just introduced for the membrane method, the difference in the pressure is very important, but the concentration is very low, 0.04%. That means the pressure difference is very small. Therefore, therefore, the amount of the CO2 that passing through the membrane is very small. In order to process a large amount of the CO2, that requires a huge area of the membrane. This is unusual size of membrane we require to process such large amount of CO2. That is why this the membrane method is not recognized as an important technology for DAC. But the issue here is the low permeability of the gas. That is the issue with this membrane method. Therefore, we started to think we have to, or we can improve the efficiency of permeation. Then we can use this membrane method for DAC. So that is how we have started our research. So the permeability is a negative response to counter response to the thickness of the membrane. So the thinner the membrane, the higher the amount of permeation of the gas. This is a very simple relationship. So this is the challenge we have to cope with. What the membrane that has been reported as the most performing in terms of gas permeation, we try to make this membrane, the existing membrane, further thinner. So this is what we have developed. This is the thickness is 34 nanometers, 3,000 times thinner than food lab, or even thinner than the COVID-19 virus. So this very thin film is installed here. By use of this membrane, we are able to dramatically improve the permeation efficiency of CO2. So the efficiency is 20 or 30 times higher than previously reported the cases of our highest performing membrane. So using this the membrane, then we are able to capture the CO2 from the atmosphere. This is what we have realized. So this is the experiment. It may be find it difficult to understand. So, but this is a cross section of the membrane, and this is the cell for permeation of the gas. So from here we put the CO2 0.1%. And then this is the membrane, and then the CO2 that passing through the membrane, and also the CO2 which does not permeate the membrane. We have analyzed using gas chromatography in order to identify how much the CO2 is permeated. So generally the thickness, general product of the membrane is the 3 nanometers. And in this case, the most of the CO2 does not pass through. But if the thinner membrane I introduced is used, then 1/4 of the CO2 pass through. Also, 75% or remaining CO2 is not captured. But in terms of efficiency of permeation, efficiency has become 3 or 4 times higher. So this is a significant result. And I'm quite sure that is the successful cases where we are able to shift the CO2 from the gas which is close to the atmosphere. So we have found this test result is kind of the example we can think of the practical products. So I think you see the air conditioner, and the air conditioner has a film. So the membrane is a kind of a film of air conditioner film, so very simple and inexpensive, and no toxic chemical is used, and no site limitation for installation, and the size is adjustable. So we can increase the membrane area by changing the size. So in the cities, there is a kind of limit for installation place, but liquid solution practice in the Western countries, they are large size, but this is not applicable to the city area. And this is the relationship. So relationship between the thermal power plants and the photovoltaic power production. The thermal power plant is the plant that generates the power on a large scale. On the other hand, there is a distributed type of power generation, which is PV. So you can install the PV, the station, and you can generate the power anywhere and where it is needed. So the same idea applies to the DAC. We can have large-scale CO2 capture like the one shown on the right top. And also we can have a distributed type of the DAC system. So this is the one type we are thinking. So this is about the on-road CO2 emission in US. So the red area indicates the area that have the lot of the CO2 emissions. So as you can see from these pictures, the urban areas, the lot of CO2 has been emitted. So, but it is very difficult to install the large scale carbon capture system in the city area. Instead, we can use the distributed type and the small size DSC system in the city area in order to capture CO2 from roadside. Therefore, this is a very promising technology for city area. And the one thing we have to think about as a one set of the solution for CO2, we have to think about what to do with the CO2 after capture. So this is the idea, CCUS, or carbon capture, utilization, and storage. So all these processes have to be considered as a one set. So for capture, there are two types, utilization and storage, or the very captured CO2 underground. And if the CO2 is used, there are many ways to use the CO2, but in recent years, the attraction is drawn to the direct utilization of CO2, such as the chemicals and the fuel. So research on the utilization of CO2 is actively going on around the world. Of course, the research institute, Professor Yamauchi and Professor Paul Keynes, who is also the professor for Kyushu University. So they are working on the research to convert CO2 into methane, ethylene, ethanol, carbon monoxide. They are successful in miniaturizing or downsizing the device. In particular, Professor Yamauchi has developed this the catalyst so that the CO2 can be converted with the low amount of energy. So the technology to selectively the CO2 at a low cost has been already developed. So this is a separation membrane, and the conversion units are connected like this. So from the air, CO2 is absorbed and then separated in this unit with the separation membrane, and then collected or recover the CO2 is a electrochemically process to convert into useful material. So this is the idea we are now working on. So in this way, the CO2 is collected from the air and then can be converted into useful material, gas or fuel, and so on. So this kind of the small size of devices can be installed across the town, and then the CO2 is captured from the air and then converted is the carbon resources. So local production and local consumption or carbon recycled society can be created. So to make this idea realized, we collect the CO2, and we can decide how much CO2 has to be captured and consumed using this kind of Lego block like the DSCU system. Of course, there are many other the technical issues we have to tackle. So that's why we have joined this Moonshot project. We are working on high-risk, high-impact R&D. This is a very ambitious goal we have set, but we work with the professors or the researchers across Japan and overseas or United States in order to promote R&D, in order to create the cycling the economy. So this is the last message I'd like to convey. CO2 has to be reduced because CO2 is the source of global warming. But at the same time, CO2 is a very important the resource for humankind. So you can see the background, the trees in the forest. So this is the very good system we have to come up with because the trees capture air from the air and then consume the CO2. So this is the super local consumption and the production system is realized by the trees in the forest. And the air exists around the world, ubiquitous. So we have to capture the air anywhere, anytime. Ubiquitous capture of the CO2 is very important. That's why we are working on this idea, the CO2 capture, in order to create a recycling society in the future. Thank you very much for your listening.
Thank you, Professor Fujikawa, for the insightful sharing.